In our past lectures, we saw theoretically how eigenvalue and eigenvectors emerges, and in this video we are going to see some examples, that is explicit examples, how we can determine them. So recall that we are considering a finite dimensional vector space, so our operators will be matrices. So let me just write it down. Operators are matrices in the finite dimensional case. And with that, let's begin. So let me define a matrix that will serve as an operator as well. And this is a rotation operator about the x-axis with an angle pi by 2, and it's given by 1 0 0 0 0 minus 1 and 0 1 0, and we ask what are the eigenvalues of this operator, and what are the corresponding eigenvectors. So let's try to answer them. If you recall that the eigenvalue equation will be something like this. Okay, so let's not denote the identity by this, rather this one. This was our eigenvalue equation, right? And from our previous lecture we know that the condition that of r minus omega identity equals to 0. This should help us in getting the eigenvectors. So let's try to write this r minus omega 1 down explicitly. So r minus omega times the identity will just be, first you write this r again, that is 1 0 0 0 0 minus 1 and 0 1 0 minus omega times the 3 by 3 identity matrix. Note that I'm not writing the zeros explicitly over here, but you can do that if you want to. And in the next line, this is fairly simple. This is just 1 minus omega 0 0 0 minus omega minus 1 0 1 minus omega, right? And now what you have to do, you have to calculate the determinant of this matrix. So calculate the determinant. So the determinant of this, that is r minus omega 1, will be, first take 1 minus omega, and this is just omega squared, and there will be a plus 1, so this is omega squared plus 1, and all of these are 0, so this will be 0 times this 0 minus times minus omega. But here, since these are all zeros, all these entries will be 0, and we have to set this determinant to be 0 as well. So this will give me 1 minus omega times omega squared plus 1 equals to 0, right? And from here we can conclude that omega is equals to 1 or omega squared plus 1 is equals to 0, which will correspond to omega equals to plus minus I. This I is our imaginary number, So we have three eigenvalues, that is omega will correspond to 1, I and minus I. So these are our eigenvalues. And now comes the job of finding the eigenvectors. And to find the eigenvectors, we need to use this equation, but in a new manner, that is just pulling the omega 1 to the left hand side. So let me write it down over here. To find, now we want to find the eigenvectors. So again, write down the eigenvalue equation. And then you can write it as r minus omega identity with v equals to the null vector. And here now we can go on to this explicit representation. So this will mean that I have to do the following. That is, I'm writing this r minus omega identity first. It will be 0 minus omega minus 1, and there will be 0 1 0. And this v, it will be a column matrix because we are doing a standard matrix multiplication over here. So you can guess the fact that this v is a column matrix, because that's how we represented it gets. And you can take them to be in general any symbol you want. You can take x, y, z. For convenience, I'm taking x1, x2 and x3, but it's up to you, whatever you want to call them. And this is our null vector, so this will be 0 0 and 0. So technically now you have to find out some more column matrices in terms of x, x1, x2 and x3. So let's try to do it, but the idea that will be helpful and is essential for finding the eigenvalues, I mean eigenvectors. Oops, I made a typo over here. There should be a minus omega. As I was talking about, the essential idea behind finding these eigenvectors will be to solve these equations, that is solving for x1, x2 and x3. And let's see. And for each eigenvalue, we expect to find an eigenvector, because you see there are three values of omega, so there should be three cases for this equation. Let's call this equation 1. So first we want to try with omega equals to 1, and we have to put it in this equation, that is putting omega equals to 1 in equation 1, we get 1 minus 1, then we will have 0 0, then I'll have 0 minus 1, because omega is equals to 1 and it came as minus omega, so this is just minus 1. There is another minus 1 over here. 0 1 minus 1, and you will have x1, x2, x3, which will be equals to 0 0 0. Now if you carry this out and equate the components on both sides, you will have, okay, let me just write down another step so that you can understand it perfectly. And now if you want to solve for x1, x2 and x3, you can see that the first column for the left hand side will be 0. The second, not the first column, sorry, the first entry of the column will be 0, because 0 times x1 is 0, 0 times x2 is 0, 0 times x is 0, and then you will have minus x2 minus x3, and there you will have x2 minus x3, and the right hand side is just 0, 0 and 0. Now if you compare, the first thing we get from here is that 0 equals to 0. The second thing we get is that minus x2 minus x3 is equals to 0, and the third, from the third part, that is this one and this one, we get x2 minus x3 equals to 0. And recall from our first week's lecture that this column over here, since we have three variables, it will correspond to x1, it will correspond to the second one will correspond to x2, and the third one is kind of corresponding to x3. That's how we thought of these things. And here for this x1 we have a 0 equals 0. So this introduces some freedom in x1. So this means x1 is arbitrary. That means I can take any values of x1 I want. Alright. And from the second equation over here, okay, let me just give them some name. Let's say equation A, equation B, and equation C. So from B we get x2 equals to minus x3, right? This is one condition that we are getting. So let me just mark that. And finally, from equation C, we are getting x2 equals to x3. So what does this mean? This means x2 and x3, both of them are 0, because if you just take a look at these two equations over here, from this part over here, let's call it equation, I don't know, let's call it Roman 2, and let's call it Roman 1. So this guy tells you x2 and x3 are equal, but if you put 2 into 1, so putting 2 into 1, you'll have x2 is equals to minus x2, right? Because this equation over here is telling you x2 and x3 are equal. And finally you can conclude x2 is 0, and then by equation 2 or by equation 1, whatever you like, but appropriate choice is equation 2. That is, when you have this x2 equals to 0, you can also see that x3 is also 0. So we have all the informations that we needed. That is, we found out about x1, so this is arbitrary, I can take any value I want. Then I got x2 and x3 to be 0. So the eigenvector corresponding to eigenvalue omega equals 1, that is when the eigenvalue is 1, will be, let's denote it like this, or let's write this as v1, will be just x1, and x2 is 0, x3 is also 0, and x1 is arbitrary, right? And what you can do right now is that you can take, I mean, at this point you are done, you are technically done. That is just finding this thing, you are done. But we can do better by normalizing the eigenvector. So if you are asked to normalize the eigenvector, let's call it v1 prime. That means it has a unit norm, and this will be just v1 divided by the magnitude of it. And recall, the magnitude was given by the square root of the inner product of v1 with itself. Sorry, it should be an 1. Yeah. So the idea here for normalizing this thing is that you can either take x1 to be 1 and then find the normalized eigenvector. Alright, or you can just leave x1 as it is, and then if you calculate the inner product, this will be just x1 squared, and if you take a square root of this whole thing, this is just x1. And now the normalized get or normalized eigenvector v1 prime will be given by 1 upon x1 times x1 0 0, which is just 1 0 0. So this is one of the eigenvectors, and from now on we will try to find the normalized eigenvectors, because in physics we often need normalizing of the state, so it's a good practice to use the normalized eigenvectors as well. So now what we want to do, we are done for omega equals to 1, and we had two other eigenvalues, right? One was plus I and the other was minus I. So where was that? Yeah, plus I and minus I. So let's now consider the case where omega equals to I, and when you consider omega equals to I, the equation will look like the following. That is the equation we dealt over here. Okay, so yeah, this one. Again, we have to use this equation, or so to say this equation here. So when omega equals to I, you need to write down the matrix itself. Okay, let me choose another color. So this will be 1 minus I, then you will have a 0 0, this will be 0, then you will have a 0 minus I, and you will have a minus 1, and then you will have a 0 over here, 1 over here, and another 0 minus I over here, and finally you will have x1, x2 and x3, and this will correspond to 0 0 0 right hand side. So the calculational procedure is same as before, so let me just write this down. This will be 1 minus I times x1, the second one will be minus I x2 minus x3, and the third one will be x2 minus ix3, and on the right hand side it's just 0 0 0. So now you have to equate this guy with this guy. So this is just again ordinary matrix algebra. So the first component will give us 1 minus I x1 equals to 0, and this means x1 minus I x1 equals to 0. And if you are a bit familiar with complex numbers, then you can say the real and the imaginary part get separated and both of them are 0 individually. As a result, x1 itself is 0, or from here you can just say, okay, I got some number over here and it's multiplied with x1 and I have a 0, so x1 in either way is just 0. Okay, now let's consider this equation, that is the second equation over here. This guy gives us minus I x2 minus x3 equals to 0, and this will tell us that x3 is equals to minus I x2, right? Or you can equivalently write x2 equals to x3 divided by minus I, and if you just simplify it a bit, you can write minus I squared over here, that means 1, and x3, and you have a minus I over here, and finally you have I x3. So you are writing x2 in terms of x3. And if you consider the last equation, that is this one. This will just tell you straightforwardly that x2 minus ix3 equals to 0, which means x2 is equals to just ix3. So notice that in both of these cases we had 3 equations, but not truly, because 2 of the equations are giving us some unique informations. Another one is redundant. So in general, most of the time, assuming there is no degeneracy, and what is degeneracy we will not talk about in these lectures but later. So whenever in general there will, if you have a n cross n system, that is a n cross n matrix, in general there will be n minus 1 linearly independent equations. So that means n minus 1 equations will give you some independent information, and there will be one equation that is just redundant, that is that will just give you some result that you already obtained before. So for now, let's write our eigenvector. So since we are considering the eigenvalue I, let's just write it like this. When omega equals to I, this is our eigenvector, or you can just write it like this as well, any notation you want. And here we have our x1 to be 0, right? And x2, let's write x2 as x2. Sorry, not x2 as x2, my mistake. x2 came in terms of x3, right? So let's write that. Instead of x2, write ix3, and write x3 as just x3 itself. Now the most easy way to normalize this thing is to just take x3 equals to 1. You can take anything you want, or you can just leave x3 as it is. In fact, let's work with x3 as it is. So again, just compute the norm first. Okay, let's just compute the inner product first. Up to this point you are done, but now we are just normalizing this whole thing. So the inner product is just minus I square x3 square plus x3 square, and you can take x3 square common, and there is minus I square plus 1 square. This is just 2 x3 squared, and the norm is defined as the square root of the inner product, right, of the vector with itself. So this is just square root over 2 times x3. So the normalized eigenket will be, let's call it vi prime, and this will be given by v of I. That this I actually means the notation I am using in this video, that is when our eigenvalue is the imaginary number itself and divided by the norm, right? That is, you take the vector, you divide it by the norm, so that this normalized eigenket will have a unit value. So let's write it as square root over 2 x3, and this was just 0, I x3 and x3. So now this is equivalent to just 1 upon square root over 2, 0, I, 1. And a similar calculation for omega is equals to minus I will yield omega is equals to minus I, and the normalized eigenket will be something like 1 by square root over 2. It will be 0, minus I, 1. So the eigenkets are one of them is just 1 0 0, one of them is square root over 1 upon square root over 2, 0 I 1, and the other one will be 0 minus I 1. And you can check that all of these vectors are, that is all of this eigengets slash eigenvectors are orthonormal or orthogonal to each other. So why am I saying orthonormal or orthogonal? Because in either way, the inner product between them is 0. That is, if you take the inner product of these two guys, that will correspond to 0, or these two guys, that will be 0, or these two guys, that's 0 as well. So the reason we are saying orthonormal over here, because I am using the normalized get, and orthonormal means you have some vectors whose inner product are 0 and they have a unit norm. So this is just some terminology, but the main idea is that whenever there is no degeneracy, something we are not considering in this video, your eigenvectors will be orthogonal to each other. And one important thing to note about eigenvalues is that eigenvalues are basis independent. So this is a very important thing to remember about eigenvalues, because if you have a similarity transformation, something we haven't discussed yet in our videos, but from your assignments, you have seen that under some similarity transformation, the trace or the determinant, they don't get changed. And what we will see in the future lectures is that eigenvalues will be basis independent. So that's why they will be very important to us. And let's consider another short example that will be I won't be able to show the full details, but let's try to consider a short example, and just to make the calculational procedure clear, let's say you have a matrix of 1 2 3 1 like this, and you denote the eigenvalues as lambda, and you want to find the eigenvalues and the eigenvectors. So again, the idea is to just subtract from the diagonal elements, and then we want to have the determinant of this to be set to 0. So if you just do that, this is just 1 minus lambda squared, and instead of 3, let's just take 2. I don't want to take 3. I can take 3, but let's say I don't want that right now, just for the sake of simplicity. This is minus 4 and this is equals to 0. So this will tell us 1 minus lambda is equals to plus minus 2. So lambda will be 1 plus minus 2. So that means lambda will have two values, that is 3 and minus 1. And if you proceed as before, so for lambda equals to 3, we will have 1 minus 3, 2, 2, another 1 minus 3. So you will have, there will be x1 and x2, because this is a 2 cross 2 system, so we expect our eigenvectors to have 2 entries in their columns, and there will be 0 0 over here. And finally you can see that there will be minus 2 over here, minus 2 over here, and all of these entries are 2, so let's just take 2 common, and you have minus 1 1 1 minus 1, and x1 x2, which is equals to 0 and 0. And if you again multiply this, you will have these two conditions, minus x1 plus x2 equals to 0, and x1 minus x2 is equals to 0, and both of them correspond to the same thing, that is x1 equals to x2, right? Because from this equation over here you are getting x1 equals to x2, and from the second equation as well. So this again reflects the comment that whenever there is no degeneracy, if you have n cross n system, you should have n minus 1 linear independent equation. We have a 2 cross 2 system, so n equals to 2, and we have 1 linearly independent equation. So since we have x1 equals to x2, we can write our eigenvector for, let's say, lambda equals to 3. Lambda equals to 3. Let's call this vector as 1 with some ket notation. And we have x1. Since x1 is equals to just x2, we can write it as x1. And you can just normalize it. And if you normalize it, this will be just 1 by square root over 2, 1 by 1. This is one of the eigenvectors, and another eigenvalue was -1. So let's try for lambda equals to -1, and now you will have 1 plus, because it had the following form over here, that 1 minus lambda, right? So lambda is equals to -1, so that should give me 1 plus 1, 2, 2, and 1 plus 1. So again x1 and x2, and you have a 0, 0 over here, and you will have 1, 1, 1, 1 over here. 2 is factored out, x1, x2, 0, 0. And if you multiply again, this will just give you x1 plus x2 equals to 0. The second line will give you the same thing, and these two correspond to there should be a 2. x1 equals to minus x2, right? So writing the eigenvalue for lambda is equals to 2, lambda equals to -1. Let's call it as ket2, and it will be x1, and x here instead of x2, since we got x2 is equals to minus x1, we are going to just write minus x1. And if you normalize it, that is after normalization, this is just this. So this is how you can find eigenvalues and eigenvectors of a given operator that is represented with matrix. And you might ask, why are we writing this x1 and x2, right? Because if you just look at our eigenvalue equation, this one here we are writing in terms of the abstract notation. But since we are dealing with a finite dimensional case, we can represent our operators as matrices and our kets as column vectors. So the idea for writing these columns as x1, x2, and x3, because these are variables that we want to know. So these are our unknowns and we want to know them. So that's why first we are finding out the eigenvalues, and then we are finding out, once we are done finding the eigenvalues, for each of the eigenvalues we are finding a corresponding eigenvector. Alright, and again, if you recall that these eigenvectors are the vectors that just get scaled. So for example, in the last example we saw that this is the eigen get when eigenvalue is -1. So how can you verify that? So our operator was something like this, right? This was 1, 2, 2, 1. So this was let's call it a 1, 2, 2, 1. This is our operator, and let's call this get 2 like we used to, and we want to see what happens when a acts upon 2. So 1, 2, 2, 1, and this is a normalized eigenket, so let's take it 1 minus 1, and you can just write the scalar in front, it doesn't matter. So let's see what happens. So 1 times 1 is 1, 2 times -1 is just -2, so this is just 1 minus 2, and then you have a 2 minus 1, and this is just 1/2, square root over 1/2, and here you have a -1, and here you have a +1. So see, if you just take the minus common, that is -1, if you bring this out and you plug this whole thing inside a, let's say, a parenthesis, just to distinguish. But this is what we started 2 with this, right? 2 was defined as this whole guy, that is, let me just write it down again for your convenience. So we started 2 with this. Oops, sorry, there should be a minus sign over here because I'm taking the minus common. So yeah, 2 as 1 -1, right? And here you just have a -1, and the column with the 1 upon square root over 2 is just giving you back the same vector, but it's now rescaled. So this is exactly what our eigenvalue problem told us, that these will be the vectors that will just get scaled, but they won't mix up, or the components won't mix up in such a manner for this case. So this justifies that whatever calculation we did from theoretical perspective and from these examples are correct, and they do satisfy our eigenvalue equation. And this will be it for today, and I'll see you guys on the next lecture. Thank you.